So at this point, your KSP, this concept is kind of going to be very, very, very similar to what happened with KA and KB. We're just going to kind of change the prism through what we wrote. So if you look on page 1082, the back of your book, this appendix D, you have a chart that shows different KSP values. Okay? Now, if you look on this chart, all the KSP values are very small numbers. Okay? This is going to be important. So in that regard, it's similar to what Ka values are. Ka values are very, very small, right? Okay, so if you look at how you calculate Ka values, which are hydronium ion concentration times your anion concentration divided by the concentration of the acid. Okay, and that was a small number. So mathematically, the only way you can make a small Ka value is if the hydronium ion concentrations were really small relative to the concentration of the acid. Okay? It's the only way you can make a small value. So we're going to deal with magnesium hydroxide. So if you come over here and you can look up the formula for magnesium hydroxide, MgOH2, and it is a KSP value of 1.8 times 10 to the negative 11. Okay? So what that means is however we calculate this, it's going to be a small number. Okay? It's going to be a small number, just like Ka values. If you look at that chart, you're never going to find big KSP values. They don't exist. They only exist as small values. So here's what we're going to do. This is how this is different than how Ka works. Similar type idea, but yet vastly different. So I'm going to take it deeper. To that, I'm going to add some sodium hydroxide. Okay, so 1 molar sodium hydroxide. I'm going to pour that in. Okay, so there we go. Now, to understand how KSP works, you have to understand what the molecular form is of these ions. So you have sodium hydroxide. Sodium hydroxide is soluble or insoluble?
Soluble because it's a salt.
Yeah, okay, sodium. All group 1 elements are soluble, right? Okay. So what that means is that inside that bottle, I have sodium ions and I have hydroxide ions. Okay? Now, technically these are bound up to water molecules. So here's your oxygen, and that's holding that sodium. And then the hydroxide, which is negatively charged, is attracted to this. So this is important. When I mix this up, when I make up all these solutions of sodium hydroxide, I go to the storeroom and I pull out a bottle. And sodium hydroxide exists as these white pellets. Okay? They're white. They're bound together. They are bound together. Okay? They exist as a solid lattice of sodium and hydroxide. They're bound together. They're locked in. You put them in the presence of water. Okay? And this is a tug of war. So the sodium and hydroxide, they're going, hey, tight. We've been sitting in that storeroom for like maybe 5-6 years, chilling out. Okay? This is our moment to shine. We're tight, close. And you put them in the presence of the water molecule. And now they're conflicted because they're going, man, I'm attracted to the sodium and the hydroxide because they've been together. That's what allows them to exist as solid. The only way they can exist as solids is if they're attracted to each other. Now, you put them in the presence of water. All group 1s are soluble, right? So basically what that means is that they turn traitor on each other. Go, hey, love to stay and chat, deuces, we're out. So the reason that they become soluble is that the attractive forces between the sodium and the water, and between the hydroxide and the water, these bonds that form here are stronger than the bonds that hold them together. Okay? If those bonds weren't stronger, they would be insoluble and they would exist as they wouldn't dissolve. So you go to wash your hands. Okay, great. Water polar molecules. your skin is made up of atoms. Your atoms, the electrons and protons and everything that make up your skin, are attracted to the water molecule. Now, conveniently, the bonds that hold your skin together are stronger than the bonds to the water. Because if they weren't, what would happen to your skin?
Dissolve.
It would become soluble in water. That would suck. It's like, did you wash your hands? No, really? If you had, your skin would have been gone.
Why do we use soap?
Wait. Soap breaks the bonds that hold the particles to your skin.
All right.
Completely similar but different. Okay. So, what happens is that the sodium and the hydroxide, which is important, they're existing as ions with water. Now, we typically don't worry about the water. It's there, but we don't worry about it because it just muddies the water. Now, the same thing is true of magnesium nitrate. Okay, great. So I've got magnesium ions, which are 2+ because they're in group 2, right? I got nitrate ions. All nitrates are soluble. But again, magnesium nitrate, oddly enough, is a white powder. You see the recurring theme. Take the magnesium nitrate, I put it in the water, boom, it dissolves. Bonds with water molecules are stronger than the bonds with magnesium and nitrate. They turn coat, hey, we're out, swipe right, I found somebody new, not going to hang out with you anymore. Now, I'm going to mix them together. So I've got sodium hydroxide in here. I'm going to add some magnesium nitrate to that. So when I add that magnesium nitrate to that, please, I get this heavy white, kind of milky precipitate. Okay? So something changed, right? Something changed. So I went from having free ions into something that's solid. So we're going to look at our options. So only thing I'm going to focus on are the magnesium ions, the nitrate ions. I'm not going to worry about the water, and the sodium ions, and the hydroxide ions. Okay? So inside the beaker, I've got these 4 ions available. Do you think the magnesium is going to bond with the sodium?
No.
Absolutely not. Why?
They're both pluses.
Both positive charges. Nitrates are not going to bond with the hydroxide. That's not going to happen either. Those are both negatively charged. Now, the magnesium could become attracted to the hydroxide, and the nitrate could become attracted to the sodium. So in the Chem 1 version of this double displacement reaction, in the Chem 1 version of this, you would write, oh, I'm a Chem 1 student. That's magnesium nitrate and sodium hydroxide. And oh, and it's a double displacement reaction. And you get magnesium hydroxide and sodium nitrate. And you balance it and you go, oh, I've got 2 of those. And I'll put a 2 there. Wow, yay for me, I'm a Chem 1 student, right? I wrote and balanced the chemical equation, okay? And then you go to the lab and you mix these 2 things together and go,
Yeah.
okay? And you felt really cool, okay? And you did. That was the Chem 1 version of what happened. The chemistry version, we need to take this to much deeper depth. So, when you make the sodium nitrate, could that potentially be the precipitate?
No.
Absolutely not, for 2 reasons. Why?
They're both soluble.
All nitrates are soluble, and all group 1 elements are soluble. You couldn't make sodium nitrate be the precipitate if you tried. Okay? Literally, if you tried, you could not do it. Okay? It's just like, no way. I'm much more happy with the water molecule. I'm like, no, not even just friends. No. Okay? So what that means is that after this reaction takes place, the sodium ion is still existing as sodium ions. The nitrate ions are still existing as nitrate ions. Cool. Okay? So what happened is that the magnesium ions went from being magnesium ions floating around, free spirit, look at me, and then it got hooked up with hydroxide. Now, the opposite happens here. the bond between the magnesium and the hydroxide is stronger than the bond with the water molecules. So they leave the water molecules and go, wow, let's hook up. Okay? So they swipe right. Okay? They hook up. So the magnesium ions hook up with the two hydroxide ions, and we make NgOH2. Okay? Now, listen to me. This is the net ionic for the formation of the precipitate. And this is all about net ionics. Okay? Listen to me, Isaac Bruce. Isaac, this is not done by marking through things. Okay? You rewrite these. So the net ionic has to be balanced on two things. What are the two things it has to balance on? Charge and number of particles. Here's what you don't do. Don't go in here and put, oh, magnesium. Is magnesium written like this the same as Mg2+?
No.
No. If you put Mg, I'm going to think that's elemental magnesium. I'm going to think, y'all have seen elemental magnesium, little thin magnesium ribbon. Okay? Right?
It burns bright.
Yeah, it burns bright. This is not this. Okay? They are vastly different. Magnesium and magnesium ions are vastly different things. One's a bright ribbon. This is an ion attached to a water molecule. Okay? They are not the same thing. This has the magnesium has an equal balance between Chihuahuas and St. Bernards. The Mg2+ has a deficiency in two Chihuahuas. Okay? Not the same thing. Vastly different. Now, listen to me what I'm about to tell you. This is the net ionic for the formation of the precipitate. Okay? So this is making the precipitate. Okay? This is making the precipitate. Now, with Ksp and any solubility, this is not what we need. Okay? This is for the formation of the precipitate. And this is where everybody gets this wrong if you don't understand how this is calculated. So if you look at this, what's going to happen is this. Here's this solution. You made a bunch of solid magnesium hydroxide. That's not the story. The precipitate is not the story. The story is up above. The story up above is that there is a certain amount of magnesium ions and a certain amount of hydroxide ions that are still there. That's the story. Okay? So if you understand the shift in the story from the precipitate to the ions, then you can understand Ksp and Qsp. Okay? Qsp is just like a snapshot. Ksp is when it's in equilibrium. So when you're talking about these solubility products, do not focus on the precipitate. Focus on what's happening with the ions up above. So what's going to happen is this. We need to shift our focus and reverse that reaction. The focus is becoming magnesium hydroxide turning into magnesium ions and 2 hydroxide. This is what we need to focus on. We don't need the formation. We don't need to focus on making the precipitate. We need to focus on, hey, this magnesium hydroxide could dissolve and make a certain magnesium ion and a certain amount of hydroxide ion. So here's what's important. Ksp, we're going to follow the same format. It's going to be products over reactants. But we're only going to deal with concentrations. Okay? This is a solid chunk at the bottom. I can't talk about the concentration of the chunky stuff because it's a chunky stuff. Okay? It's not dissolved as ions. There's no molarity to talk about. So we don't talk about that. So just think, what about the magnesium hydroxide? Okay. Now, in contrast to that, if you have HA and you have hydronium ions turning into anions, you worry about all 3 of those because you can talk about the concentration of the hydronium ion. You can talk about the concentration of the anions. you can talk about the concentration of the acid. Okay? All of those are measurable things because they're all existing in a solution. Okay? But when you talk about Ksp, the magnesium hydroxide, like, what happened? Okay? So never speak of the solid form. The only thing we focus on are the ions. So my Ksp, just like over here you have the hydronium ion concentration times the anion concentration, this is going to be the magnesium ion concentration times the hydroxide ion concentration. But wait!
Oh dear.
There's a twist. We have this 2 in front of here that we didn't have before. Okay? Now, this has to do with something called the solubility product and how this whole thing works. So here's the rule. Whatever coefficient is in front of the OH, that tells you that this thing is going to get squared. Okay? If there was a 3 in front of it, that concentration would get cubed. Okay? Now, in acid-base stuff, you never had to worry about that because all the coefficients were just 1. Okay? With Ksp, a lot of times, they're not equal to 1. So here's the golden rule. It's a simple rule. There's nothing complicated about it. It isn't like calculus where you have to like decrease the exponent by 1 and multiply in front of it and, you know, all of this good stuff. It's as simple rule as you can possibly get. Whatever the coefficient is in front of it, that's what you raise the exponent to. Okay, that's it. Okay, do not make this complicated. Now, here's where we go back to the same idea. So if you look at the Ksp value for magnesium hydroxide, that was like 1.8 times 10 to the minus 11. Okay? So what that means is this. And this is where these are similar ideas. And if you understand the bigger picture, this is the same idea, just slightly repackaged. So all this is, in this situation, is that means when I take the magnesium ion concentration times the hydroxide ion concentration squared, Mother Nature wants 1.8 times 10 to the minus 11. That's it. Okay? That's it. That's what Mother Nature wants. Just like if it was a Ka value, Mother Nature would want the hydronium times the anion divided by the acid equal that Ka value. Mother Nature in this situation wants the 1.8 times 10 to the negative 11. When you multiply these values together, Mother Nature wants that number. That's when Mother Nature is in equilibrium. Okay. Now, with all that said, I want you to imagine this. We're going to take it like a 1 liter container. Big, massive, lots of water, 1 liter. Okay? And what's going to happen is that I'm going to take some solid magnesium hydroxide. Okay, this is important. I'm going to take some solid magnesium hydroxide, tiny bit of it, and I'm going to mix that into the water. Okay? So what's going to happen is that that's going to dissolve. I want to make some magnesium hydroxide. I want to make some magnesium and some hydroxide ions. Now, technically, we're going to get 2 hydroxide ions for every 1 magnesium because it's MgOH2. Okay? So this reaction is the dissolution of magnesium hydroxide. Mg ions, and we're getting 2 hydroxide ions. So basically what's going to happen is this. Mother Nature is going to allow this stuff to dissolve until the concentration of the magnesium ions and the concentration of the hydroxide ion squared equals 1.8 times 10 to the minus 11. Now, after that point, Mother Nature goes, hey, I'm full. I can't handle anymore. Okay? I'm maxed out. So if you add any more to it, Mother Nature goes, I can't handle you as ion. You have to exist as a solid. So it would be somewhat analogous to this. Okay? I walk into this room. I have an equilibrium value of, say, 15. Okay? That's the most I can handle with kids moving around. Okay? So I walk in, it's after lunch, some of you are starting to filter in. I got 7 kids, I got 10, I got 12. Okay? I can handle you all milling around. Okay? In equilibrium, it's floating around. Okay? You're dissolving, you're existing as ions. Okay? And I hit 15. And my K value is 15. At that point, I'm at equilibrium. So this is when I'm cool. I've got 15 kids, and I'm cool. This is my equilibrium value. This is what I want. I want 15 of you milling around. That's what I'm having. Now, 3 extra kids walk in. I can only handle 15 of you milling around. What am I going to do with the other 3 kids? Okay, that got violent really fast. How about I just make them sit down? Okay, I'm going to make them be the precipitant. Okay, so 3 extra kids walk in. I can't handle these as ions. I'm going to make them sit down. Now, one of them says, "Ah, man, I'm going to stand up." Okay, great. One of the kids stands up. What that means is that one of you then has to sit down because I can only handle 15. So as more and more kids come in, what's going to happen to the number of kids that are sitting down? It's going to increase because I can only handle 15 of you up moving around. Any additional kids that come in have to be seated as a precipitant. They can't be up moving around because I can only handle 15 kids up moving around. Anybody else can be in the room. I'm not saying you can't be in the room. I'm just saying you can't be up moving around. Okay? Got that visual. Now, Mother Nature sits here and says, okay, I'm going to add this magnesium hydroxide too. This is like you all walking into the room. At some point, mathematically, the magnesium ion concentration times the hydroxide ion concentration is going to get that number. At that point, if I add any more to it, it can't dissolve because I've reached that point of equilibrium. Now, if you look at Ka values, some Ka values are exceptionally small, like maybe 10 to the negative 25th. Okay, really, really small, like 10 to the negative 25th small. Okay, so if something's 10 to the negative 25th, what do you know about the concentration of those ions at equilibrium? They're really, 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 really small. Like that might be, hey, Bergkamp's equilibrium value is like 3. Hey, Bergkamp can only handle 3 kids up moving around. Once that's reached, hey, everybody else has got to sit down. All right? So here's what's happening. If you look at this solution, okay, what's happened is this. I mixed those solutions together. Okay? I had a bunch of magnesium ions and I had a bunch of hydroxide ions. Mother Nature goes, whoa, stop the bus. Okay? That's like me walking in and seeing 30 people up milling around. And I'm going, whoa, stop the bus now. 15 of you need to sit down because I can't handle 30 of you moving around. And that's basically what Mother Nature did. Mother Nature goes, whoa, there's way too many ions moving around for me to feel comfortable. You can still be in the room, but you have to exist as the precipitant. Okay? So I'm not saying the ions aren't there. I'm just saying they're not existing as ions. Now Mother Nature is going to force them to come together because Mother Nature can only handle so many ions floating around. Go with this. So when you look at that chunky precipitant, I'm not saying, here's the common misconception. Everybody goes, well, there's no magnesium and hydroxide ions up above. No, there are. Okay? There are some up there. But mathematically, they produce that value of 1.8 times 10 to the minus 11. Okay? Cool with this. They're there. Now we'll do something different. Now we're going to begin to add hydrochloric acid. What do you know about hydrochloric acid? Strong acid. So how's this existence? H plus N. Fluoride. Now, I'm going to add some hydronium ions in here. Oh! Wow, that got exciting. Now, I want you to look at this. I want to add hydronium ions. Exactly as Nathan Nelson said, the hydronium ions are going to react with hydroxide ions, and I'm going to make water. Okay? Are the hydroxide ions still there?
So, none, actually.
The ones there are, but the ones that hook up with hydronium are bound up as water. They are no longer existing as hydroxide ions. Now they've become water molecules. So listen to me very carefully. So what's going to happen as I add hydrochloric acid? What do you think is going to happen to the concentration of the hydroxide ions in the solution? Oh, it's going to go down. Why? Because I'm making water. Okay? Mother Nature is going to flip out at this point. Mother Nature is going, whoa, 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 it's bad. Mother Nature still wants to be in equilibrium. But hydroxide ion concentration is going down.
So magnesium plus 2 goes up.
Oh, magnesium has to go up. Now, what's the only source?
Do we have Jordan?
The precipitate final answer.
I haven't even asked the question.
That's what you get.
Okay, what's the only source of the magnesium ion?
The precipitate.
We're to our heart. Okay? The only source is the precipitate. So what do you think, as I add hydrochloric acid, what do you think is going to happen to the amount of precipitate in here?
Decrease.
It's going to decrease. Because it has to dissolve to replenish the hydroxide ion concentration that's going down. So,
It's going to be clear.
so I'm going to add some hydrochloric acid. Okay? I need that faster.
Wow. Oh, it's going to become more clear.
Miracle of miracles. What happened?
Water.
It turned clear.
No more precipitate.
No more precipitate. Now, are the ions still there?
The magnesium ions.
Magnesium ions, right? So here's what happened. Is that Mother Nature goes, oh man, this is bad. You took away my hydroxide ions. But Mother Nature still wants to be in equilibrium. So you can think of the precipitate of magnesium hydroxide as being like a bank. Okay? So you have a magnesium hydroxide bank. So when that strong acid shows up, it reduces the concentration of the hydroxide ions. Mother Nature is sensing a deficit. So Mother Nature has to go to the bank and make a withdrawal. So now that precipitate dissolves because now that magnesium and hydroxide are turning back into ions to try and maintain equilibrium. Got the idea? Okay. So, QSP versus KSP. This is a concept we're going to use in a whole bunch of different ways. So this is important. What's the only time you use the value of K?
Equilibrium.
It's at equilibrium. That's a very, very specific time. Now, the QSP is like a snapshot. So the QSP calculation has the same form. So the QSP for magnesium hydroxide would still be the magnesium ions times the hydroxide ion concentration squared. Okay? It's the exact same thing. Okay? Mathematically, they are calculated the exact same way. But what you do is you compare the QSP to the KSP. Ksp is a one-trick pony. What's the only time that pony exists? At equilibrium. Qsp has three options. Qsp could be bigger than Ksp, Qsp could equal Ksp, Qsp could be smaller than. Now, if you calculate the Qsp and it's the exact same as the Ksp, how would you think you could describe the equilibrium? It's at equilibrium. So if the Qsp equals the Ksp, then, it's just an equilibrium. They're the same thing. Nothing's going to happen because Mother Nature's happy. Now, how you calculate the Qsp? Listen to me very, 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 very carefully. These are the concentrations immediately after the solutions are mixed together. So this is how this typically plays out. You're going to take, just like I did, you're going to take some magnesium nitrate and you're going to take some sodium hydroxide, and we're going to mix these together. So what you need is the concentrations of these immediately after they are mixed together. So let's just say that I have 10 milliliters of a 0.1 molar solution of magnesium nitrate, and I'm going to have 10 milliliters of a 0.2 molar sodium hydroxide. And I want to calculate the Qsp. So, here's the deal. I need the magnesium ion concentration after it's mixed, and I need the hydroxide ion concentration after it's mixed, and then I'm going to square those. Okay? So, here's the story. Magnesium hydroxide is going to turn into magnesium ions and hydroxide ion. Okay, so this is my reaction. Okay, need to figure out what's going to happen. So the reason that I need to know that is that I need to know if any of these concentrations are going to get squared, cubed, anything like that. Okay. Now you can work in millimoles or you can work in moles. I don't care. Personally, I work in millimoles because it makes the math easier. So I'm going to take 10 milliliters of a 0.1 molar solution. So that means I have 10, I have 1 millimole of magnesium nitrate. Now, in this situation, I don't care about the concentration of my nitrate ions. It's not part of the story. Okay? Are they there? Yes. Do I care about them? No. Okay? Because it's not going to be part of the calculation. And the same thing is true of the sodium hydroxide. So if I take 10 times 0.2, I get 2 millimoles of my sodium hydroxide. Again, I don't care about the sodium. The only thing I care about are the magnesium ion concentration and the hydroxide ion concentration. So here's the drill. This is how many millimoles I have. Okay? But I need the concentrations, it has to be concentrations because it's square brackets. I need the concentrations after they are mixed. So this is where this is the same type of thing you do, like when you completely neutralize a weak acid, and with the hydroxide it's completely neutralized, and you divide by the total volume to find the concentration afterwards. We're going to do the same thing. So what's the total volume that you've mixed together?
20 milliliters.
20 milliliters. So I'm going to take 1 millimole because I need the concentration of the magnesium ions after they are mixed. So I'm going to take 1 millimole. So somebody take 1 millimole and divide that by 20 milliliters. What do you get? 0.05. So I have a 0.05 molar concentration of my magnesium ions. Now I'm going to do the same thing with the hydroxide. I'm going to take 2 millimoles and divide that by 20 milliliters because of the fact that I need the concentration after they're mixed together. Total volume is 20.